this computer. Great. All right. Well, welcome everybody to our June AGU Geodesy early career webinar. We're so glad you joined us today. Today's speaker is Mike. I'm going to have to learn how to pronounce your name, Mike. I don't actually know. Is it Croteau?
Croteau.
Croteau. Excellent. I just learned something new. Thanks, Mike.
Yep.
Mike is speaking us today from NASA's Goddard Space Flight Center, where he is a research geophysicist. He received his PhD in 2019 from the University of Colorado Boulder, focusing on GRACE and GRACE follow-on data, which we'll hear about today. So take it away, Mike. So glad to hear from you.
Great. Thank you very much. Good afternoon, everyone. Thank you for attending this talk today, or if you're watching, I guess, sometime in the future. I want to first thank Matt and Annie Kazanov for the invitation to speak today. Also want to thank my colleagues, so especially Bryant Loomis. He helped a lot with putting this presentation together. And then all my other colleagues, both at Goddard and when I was at University of Colorado, for all their many efforts that have helped contribute to what is included in this talk. If you have seen me speak about any of the research I've done in the past, then some of this might look familiar, but I've tried to craft today's talk to be sort of an interesting higher level glimpse at lots of work that has gone into GRACE data processing, and then specifically work here at Goddard and some ongoing work that we are doing. So assuming that I am still sharing screen and all, I am going to try and just get this started. Okay, so today I want to share with you a bit of a story about the advancements in time variable gravity estimation from GRACE and GRACE follow-on. And just to give a quick preview of what I'll cover, I've provided this outline. So we'll start with just kind of a quick overview of GRACE for anyone who's unfamiliar. We'll talk about the main GRACE data products. And then one of those data products that has been really a big part of my own career has been MassCons. So I'm going to talk a bit about the history of MassCons, what they are, and then our recent work in pushing the limits of what MassCons can do. And so when we get to that last part, it'll really be my contribution in what we've been working on. So to begin, if anyone's unfamiliar with GRACE and GRACE follow-on, these are two missions that one obviously followed on to the other, but they are missions that each fly a pair of satellites in low Earth polar orbit. The two satellites are in a leader-follower configuration, so one satellite is ahead of the other one in orbit about 220 kilometers. And the original GRACE mission was decommissioned in 2017 after about 15 years of Earth observations. But then GRACE follow-on launched the following May and has continued that time history. So we now have more than 20 years. The satellites combine precise pointing and positioning measurements with an inter-satellite ranging measurement that allows us to very finely and precisely track the distance between the two satellites to micrometer precision. On board the satellites are accelerometers, and these allow us to determine non-gravitational forces like drag. And with all of that taken into account, we can then determine something about the gravitational forces that are perturbing the satellite orbits and look at how those change over time. To get a bit of an idea of how that works, I've put together this cartoon that can hopefully help explain how we can determine Earth's gravity field from the ranging measurement. So in the first box, we have the two satellites, one flying in front of the other one, taking that measurement. And as we go to the second box, the satellites approach some type of large mass. And the leading satellite is going to approach that mass first. And so it begins to accelerate towards the mass, and the distance between the two satellites starts to grow. Now, over time, that first satellite begins to pass it and will start slowing down as that large mass starts to pull it backward. Meanwhile, the second satellite is now approaching and is accelerating forward. Right about in this period is where we see the maximum distance between the two satellites. And then as they continue to fly past, they both begin to slow back down and then eventually reach back to their kind of nominal range that they had. If you then look at the fourth box, sometime way off in the future, if that ice melts, then the mass that was there that caused this perturbation will be smaller. And so we should see smaller effects on what's going on. Now to look at this more across an actual example globally, here's a plot that's provided by the GRACE follow-on science team. And it was just one of the early plots when GRACE follow-on launched, showing how inter-satellite range evolves over time. This is just for one particular orbit, but what you can see here is that as these satellites fly along, they sort of have a nominal range between them that then when they overfly large mass anomalies can get perturbed. The biggest one here on this particular example is when it overflies the Himalayas, somewhere between numbers 9 and 10 on that bottom plot. And you can really see a large effect there as the satellites fly over that range. But you also see it in other locations, and then you can kind of see where it's flying over oceans and has more of a relatively calm state. As I mentioned before, the real key kind of value add from GRACE and GRACE follow-on has been in the creation of this now 20-year record of time variable gravity. It's really important that as this mission has evolved and then the second mission follows on, we can compare what we look at now versus what we looked at in the past and see how the gravity has changed. And if the gravity has changed, we then can infer something about the causes of gravity that are changing, like surface mass. So here in this particular picture, we've removed the mean gravity field from all of the monthly solutions, beginning all the way at the beginning of GRACE through the end of 2021. And we can see that there's kind of a bluening effect, I'll say. And in this particular color bar, what that means is that the oceans, which is most of that blue there, is slowly accumulating mass, which makes sense, right? We know that there's sea level rise, and a large component of that sea level rise is by additional water being put into the oceans. These monthly estimates are utilized for all kinds of science studies. And if we look closely at them, we can begin to see some hot spots if you really knew where to look. Obviously, the Amazon is going to be a place that sees lots of rainfall, and then also has its dry spells as well. So there's a big signal there. But pretty much anywhere where there's a water signal, there is a signal that we can study with GRACE. And we do this regionally, and we do this globally. But today, I don't want to focus on the science aspects. Instead, what I want to focus on is the work that has gone on in GRACE processing and work that I have been involved with in my last few years here since I've finished my PhD in creating the products that the scientists can use to do those studies. So I won't get too much into detail about studying Greenland ice mass loss or sea level rise or drought in California. But instead, I'm going to talk about how over time we have improved the products that scientists can use to study those things. And then some of the things that we're thinking about now on how to further improve them and continue to push forward the data so that the science can continue to prove as well. And so with this particular talk, I want to focus on the GRACE data products themselves. And in order to understand how we have advanced in time, it's helpful to understand the differences in the data products. Today, I'm going to talk about kind of 4 main types of data, and we'll really focus there on the last one. But the general theme here is that the lower the level, the harder it is to work with this data, the more time and effort it takes to put into it. And then the higher level data is easier to work with and is more kind of scientist ready. So with that in mind, we'll just begin with talking about the level 1B pre-processed satellite measurements. Now, level 1B implies that there must be a level 1A. Level 1A is just the raw measurements from GRACE. And there are a certain amount of processing that is done in order to take those raw measurements and account for a few things so that then we can have these measurements that are ready to basically do science with. The measurement types that would all be considered level 1 are going to be those things I mentioned before. So the accelerometer data that measures our non-gravitational forces like drag, the positioning and pointing data from GPS and our star cameras, and then the ranging data. And on GRACE, that ranging data comes from a K-band microwave radiometer. And on GRACE follow-on, it does have that K-band ranging device, but it also has a laser intersatellite ranging device. And in this particular plot that you can see, this is from a colleague, Shinchan Han, we can see that the KBR, the kind of older school microwave ranging device that has been on GRACE and now GRACE follow-on, has a much higher amount of noise associated with it than the laser ranging device, which is shown here in red and yellow. But you can see that they actually are measuring the same signals themselves. And so this new add-on instrument on GRACE follow-on is providing an interesting opportunity for some potential new science, but not necessarily something that I'm going to talk about in today's particular talk. Taking a step up the level chart, we'll call it, is the level 2 products. Now, these are the products that have basically been being produced since the beginning of GRACE. And these are monthly, unconstrained spherical harmonic solutions. Now, these are typically monthly, but you can actually solve this on any time scale. But if you're unfamiliar with spherical harmonics, we can kind of think of these as a Fourier series expansion onto a sphere that are just a function that's representing Earth's gravity field. If you're completely unfamiliar with spherical harmonics, you probably still have heard of one of them. If you've heard of Earth's equatorial bulge, sometimes called J2. And this is the effect of the spinning Earth on Earth's mass distribution, which effectively flattens Earth. As a result, we basically see that Earth has a larger radius at the equator than it does at the poles. Now, this effect is actually described by one of these spherical harmonics, the harmonic C20, which is in the kind of second row in the middle there on that chart on the left. With GRACE, we typically estimate gravity solutions to degree and order 60 or sometimes 96. Now here on this chart, I've shown, on the left chart, I've shown out to degree and order 4, and you already see that there's, a couple dozen coefficients. On the right chart, I actually show out to degree and order 20, and you can see it starts to really balloon as you get higher and higher in degree and order. So what this means is that we're actually estimating a gravity field that's represented by as few as 3,700 coefficients, or as many as 9,400 coefficients, depending on how big of an expansion we're using. When we take all of these individual coefficients, which each describe all of these different kind of checkerboard patterns on the Earth, we can put them together, and combined, they can be used to describe Earth's gravity field using an equation like what's on this particular slide. So when we put these together, we see the combination, and these thousands of coefficients can jointly describe the gravity field. Depending on what we want to investigate, we can use the same spherical harmonic estimate to look at anything from geoid to surface mass change or vertical displacement, gravity anomalies, and certainly more. You can see from the figures here that the measurements are all related, right? We can see that there are hot spots over Greenland, for instance, in all three, but that the different maps might not correlate one-to-one with one another. And that's because they're containing different amounts of information depending on what they are trying to describe in those particular figures. Now, a big caveat with spherical harmonics and level 2 products in general is that GRACE and GRACE follow-on don't perfectly capture the gravity field, sort of to be expected. But instead, these level 2 estimates include noise and a particularly challenging problem known as correlated error. Essentially, what we have here are things that have become known as vertical striping. And if you look in the plot on the top left, you can really see these vertical stripes. They make it hard to see what's going on the Earth because of these correlated errors kind of screwing everything up. Removing these stripes, but preserving signal is sort of the whole trick. And this has been an active area of research since basically day one of GRACE. There have been lots and lots of techniques that have been developed, and here I'm just showing a couple of them. But with these techniques, we can go from the top left to, for instance, one of the plots on the bottom, and we can begin to see that there actually is real signal that's being represented there once we get rid of all that striping and noise. The problem with these processes, though, is that they're post-processing. And anytime you do post-processing, it necessarily complicates an analysis, and it destroys some potential information that's being captured by the satellites. And for that reason, and due to just the challenges in using spherical harmonics in general, these products typically carry an expert-only tag. In other words, it's hard for just an ordinary scientist who has no GRACE experience to come in and use these from day one. In order to help lower that barrier to entry, for years, the GRACE science team has been producing a second product, one that we call a level 3 product. And it's a pre-gridded, pre-smoothed, pre-processed product where they take the spherical harmonics, they apply all of the necessary corrections and things to the best that they can, and then they put them onto a grid. Now, this is a product that is commonly referred to as the GRACE TELUS grids, and it's very helpful for non-experts. It has allowed non-experts to be able to use GRACE data for a long time. But the problem is that it suffers from information loss associated with that post-processing that had to go on in order to produce this product. And it has other limitations as well that wouldn't necessarily be there if we could estimate a map like this directly from GRACE observations. And so therefore, a new type of product was introduced now well over a decade ago that spatially represents the time variable gravity field into a gridded surface mass product called MASCONs. Now MASCONs is short for mass concentrations. And basically we can think of these as a pixelation of the gravity field onto kind of a checkerboard surface on the Earth. And the key difference between this and that post-process map that we saw a second ago is that these checkerboard MASCONs are estimated directly from level 1B measurements, which means that rather than needing post-processing in order to remove noise and striping, we actually are able to estimate these maps directly. In order to make that work, the secondary benefit of using spatial MASCONs is that we can impose spatial regularization constraints, and these constraints allow us to move effects such as striping and noise, but remove them during the estimation step. And that piece is very key because it allows us to better preserve the real information by capturing all of that filtering and processing within estimation instead of in post-processing. Today, there's three main MASCON solutions. They're produced here at Goddard, as well as at JPL and the University of Texas Center for Space Research. Really, I'll just leave this cartoon as a simple example of the biggest advantage of these MASCONs. And it's in that they are so simple to use. If you want to look at, for instance, California, like in this particular cartoon, literally all you need to do is sum up all of the individual MASCONs, put them into whatever units you want to use, and then make your plot. That's so much easier than having to do any type of analysis on a spherical harmonic product like we might have had to in the past. As just kind of a comparison then between these MASCONs and the level 2 products that I talked about before, we can really see that the MASCON solutions do a much better job of signal localization, of noise and stripe handling, of reducing leakage across boundaries. And the reason why is that these level 3 MASCONs allow us to include that regularization and include any type of extra information, prior information that we know as part of our least squares estimation in order to best resolve this gravity field signal. Okay, now before I get any deeper into what we've been working on with MASCONs, I thought I'd take us on a bit of a tour. And so this is going to be a bit of a history of where MASCONs came from and how they've evolved over the past century. Now, the idea actually first came out of an effort to estimate localized MASCONs that was in a paper back in 1968 looking at the moon. The Apollo mission was orbiting the moon. They knew that there were mass anomalies on the surface of the moon, and they wanted to have the best represented gravity field that they could for being able to propagate the Apollo orbits. And so Mueller and Sjögren, which I'm sure I mispronounced, released this paper where they put point masses onto the surface of the moon, and they estimated what those masses would need to be in order to account for the Apollo orbit. The Deep Space Network tracking data was applied towards that estimation, and the set of point masses were estimated along the whole near side of the moon. Then in 1971, a second paper came out that showed that there's actually better performance instead of using point masses if you use disks to represent each of these mass anomalies instead of those single individual instances. Then fast forward a few decades, and the first application of this MASCON approach to GRACE data was in 2005 by Dave Rowlands, who is here at Goddard Space Flight Center. Now, this approach didn't use point masses or disk MASCONs, but instead related the level 1B observations into a MASCON space through a finite truncation of differential Stokes coefficients. Basically, at Goddard, we have been set up for a long time to be able to estimate spherical harmonics, like what I was talking about before. And Dave was able to leverage that capability to kind of create a two-step that relates the level 1B into sphericals and then through sphericals into MASCON space, all as one cohesive step. This first MASCON paper recovered a 4x4 degree MASCON solution around the Amazon basin, and it kind of was a proof of concept. Then a couple years later, a 2006 science paper by Scott Luchte, also here at Goddard, successfully recovered mass change for irregularly shaped basin MASCONs in the Greenland ice sheet. And this paper was important because it was the first time that GRACE data was used to show an increase in ice mass in the interior high elevation regions of Greenland. It also properly located the locations of significant mass loss along the coast, where we know today continue to be a major issue and something that's quite frequently focused on in GRACE studies. 2 years later, in 2008, Scott, again with others, estimated a grid of 2x2 arc degree MASCONs in and around the Gulf of Alaska region. These MASCONs are all equal area and equal shape. And the work was successful at correctly identifying the regions in the Gulf of Alaska that have the largest negative mass balance. So areas like St. Elias Mountain Range, which include the Glacier Bay and Yakutak regions. In 2010, a paper by Terry Sabaka presented the mathematical formulation of a 2x2 arc degree global solution. And this paper highlighted the benefits of applying a hydrology model in the set of forward models when processing the level 1 data. And this has kind of been a big moment for us because it really showed us the importance that can go into the design of our least squares process, the regularization that we use to apply, and the types of things that we need to think about in modeling and so on and so forth in order to best come up with a good MASCON estimate. 3 years later, in 2013, then, was the release of a paper by Scott Luchte and others of the Goddard 1x1 arc degree global MASCON solution. This solution continues to be the basis for the MASCONs that we produce today. It uses the same global MASCON grid. And it's the first paper that demonstrated the benefits of solution iteration on the MASCON process. And in this particular paper and solution focused on land ice mass changes. And so it was focused on the Greenland ice sheet, Antarctic ice sheet, Gulf of Alaska. And while these solutions were global, because it had this focus on the high latitudes, the constraints were tuned to really pay attention to that, but hadn't been globally optimized at that point. So there was still a fair amount of north-south striping, for instance, at some of the lower latitudes, similar to what was dominating the spherical harmonic solutions, like I showed before. In 2015, other research centers began to release their own global MASCONs. I mentioned before, JPL is another center, and they created a product using 3 arc degree spherical caps. So larger MASCONs that they then downscaled with a procedure to improve the resolution along the coasts. And the next year, University of Texas Center for Space Research published their own paper presenting their own global MASCONs. And this particular solution is actually fairly comparable to the Goddard solution, although uses a slightly different MASCON grid. And then the key difference is that they apply a slightly different regularization strategy, and that kind of highlights some of the differences that design choices can make in terms of how they recover the gravity field. And then in our lab back at Goddard, we continue to work on this and have continued to develop and optimize our products. And in 2019, Bryant Loomis and others began to push out what we'll call a new generation of MASCONs with the most complete error characterization of any MASCON product to that point, including estimates for both noise and correlated errors. Again, those correlated errors could be due to things like leakage between MASCONs, for instance. And this paper describes the core of what is still our global MASCON solution that's distributed today. So if you were to log on to our website and grab our current product, this paper largely describes what went into that product. Now, building on that work, we've continued to put in a great deal of effort to push the limits of GRACE MASCONs, attempting to improve solution resolution temporally and spatially, and then also seeking new methods that can lower the barriers to entry for estimation and improve our own processes. And so for the remainder of today's time, I thought I would try to highlight some of these recent advances. First, I want to highlight work that came out of my PhD dissertation and the first few months at Goddard as a NASA postdoc in 2019. So this was work that was published back in summer of 2020 during the height of COVID, but was largely done from 2017 to 2019, we'll say. And we created a daily GRACE MassCon solution that was an iteration of the Goddard monthly solution. We then used that to be able to try and investigate a wide host of observability questions and attempt to push the temporal limits of what we could observe with GRACE. You can see here from these figures, we were able to capture real large-scale changes in the gravity field at sub-monthly intervals, but the spatial resolution of these recovered signals was significantly less than that of the monthly solutions. And so if you look in the kind of bottom plot there, you can see on the left something that describes the spatial resolution of the daily product versus on the right, the spatial resolution of the monthly product. You can see there's a significant difference there, but they are capturing largely the same types of signals, which is important. As part of that study, we wanted to estimate the spatial resolution that could actually be recovered with GRACE at sub-monthly scales. And we did this in two ways. The first way was to develop a pseudo simulation where we modeled a known signal in a single MassCon, and then we attempted to recover that modeled signal with a daily solution. You can see in the animation here, we succeeded in recovering that modeled signal. So in the dashed line in blue, that is the modeled signal that we put into the solution. And then in red is each daily signal that was attempting to recover that solution. However, the big difference is that in our original model, we put that in as a point mass, but in how it's recovered spatially that you can see in the image there that's changing, it was actually instead recovered over a much larger spatial area. And so for this particular case in Antarctica, we recovered a signal that was originally in a single MassCon. I'm sorry, let me go back. Originally in a single MassCon, and recovered it in an area that was about 600-kilometer radius. And so that then told us we need to be able to understand how this would behave across the globe. So we did this for a wide variety of locations, not just in Antarctica, and we were able to collect statistics across the globe. And as you can see in the plots here, the best recovery did occur at high latitudes. If you think about it, for a polar orbiting satellite is going to see the high latitudes with much higher frequency, and the orbits are going to be much closer together. And then when you go to the lower latitudes, the orbits are spread out quite a bit more. And so you would expect that it wouldn't observe that quite as well. We saw that bear out. We also saw, though, that some of our choices in the regularization made a difference as well. And so areas that were closer to a land-ocean cutoff, so a coastline, actually performed slightly better than areas that weren't near that. And that was because one of our things that we put into our regularization included information about the coastlines. And so that added information was able to help us improve our solution. Now, I said we did two different tests in order to try and attempt to measure this spatial resolution that we could recover. And the second was a statistical measure of signal recoverability using something called the resolution operator. The resolution operator is something that falls out of the least squares process, and it includes information added by solution regularization. And we found that each day, we perhaps obviously see the best recovered signal resolution nearest the orbits. So if you look in the top plots, the orbits are shown in red, and you can see that the signal that's recovered underneath of those orbits is better than the signal that's recovered far away from those orbits. We also saw better signal recovery in high latitudes and near coastlines, just like we did in our simulation. Importantly, we saw that the recovered signal met the regularization limitations that we imposed, which meant that if we can improve our prior information that we feed into the system, we can directly improve our signal recovery, which is pretty awesome. If we take those two different investigations together, we can then compile the first comprehensive look at spatial versus temporal resolution recovered with real GRACE observations. So this was in our paper, and we highlight the spatial resolution for anything from a one-day solution down to what's listed here as a 60 by 60 spherical harmonic solution. That essentially means a monthly solution. And we can talk about the spatial resolution at high latitudes, mid latitudes, and low latitudes. This is a lot of information, but the one thing I'll kind of point out is that, interestingly, if you look at the daily resolution at high latitudes, it actually is quite comparable to the monthly resolution at low latitudes, meaning that these daily solutions, even though they struggle at the low latitudes, can provide pretty meaningful information comparable to what we're already used to dealing with at high latitude locations like the Canadian archipelago, for instance. The last part of this study was that we were able to provide a comprehensive look at solution error, and that includes both noise and bias due to signal leakage. We were able to demonstrate that the recovered signal to noise was pretty useful. You can see that down in the bottom left. And basically it was useful everywhere except for the most arid locations. So somewhere like the Central Sahara, our signal to noise wasn't very good, but that's largely driven by the fact that there's not much signal there. Also, we saw, if you look over on the right, is that while if we looked at individual mascons, there was a very large biasing error. This biasing error is caused by the solution not knowing exactly which mascon to put signal in. And so is it supposed to go in this mascon or one of its nearby neighboring mascons? Because of the limited amount of information that we're putting into this process, it can't always determine that. However, we don't usually look at GRACE solutions on a mascon by mascon basis. Instead, we tend to look at drainage basins of some type. We might be interested in the Mississippi River Basin, or for instance, Greenland. And when we're interested in something like that, it doesn't actually matter for us, did we get the signal in exactly the right spot in the basin, if we know that we at least got the signal into the right basin. And so what we saw in this particular study was that by and large, we do get the signal into the right basin most of the time, except for in the smallest and hardest to isolate basins. Like you can kind of see, there's a couple bright spots there in the bottom right. And that meant that this daily solution was actually quite useful for a lot of applications. Next, I want to highlight a little more recent work that I did, which was on a new mascon technique that we published in JGR Solid Earth last year, and that we've called fast mascons. I know this is probably one of the more dense slides in terms of equations and things, but really the key breakthrough here was in how we define these mascons. So when we defined fast mascons, we actually took our original rigorous mascon estimation equations, the same equations that both Goddard and CSR use to express their mascons, the ones that relate mascons through that spherical term like I talked about. And we were able to reformulate them in order to express mascons in terms of the level 2 solution and their normal equations, which is not normally something people use, rather than the level 1b ranging observations themselves. That means that instead of needing to know the 5-second interval ranging measurements from GRACE, we can actually take the kind of processed observations that are then put into a full normal matrix as part of the level 2 process and use those to estimate our mascons. The key thing here is that this reformulation is mathematically equivalent to the traditional rigorous method that we've been using for years. But by reformulating, we've decoupled mascon estimation from level 1b processing. And that's really important because that means that instead of needing one of, I don't know, say 5 or 6 centers that are really good at level 1b processing to produce mascon solutions, now anybody can produce mascon solutions because they don't need to be able to do level 1b processing. And that's a huge breakthrough. That means that instead of everyone being reliant on the 3 mascon products that are out there, if somebody had a particular use case where they wanted to create a special mascon product geared at trying to answer a particular question, they now can do it. And so here I kind of have a high level overview of the derivation there. I'll say the secret sauce was in how we applied the Woodbury matrix identity. And the derivation's in my paper if you want to go look at it. And I give a lot of credit to my co-author on that paper, Terry Sabaka, in helping come up with this new method. To test our method, we developed a proof of concept solution that uses a really relatively straightforward regularization design and utilized the ITSG GRACE 2018 spherical solution. This was an ideal solution because they distribute as open data both their solution and their normal equations, which is something that I believe all GRACE processing centers should do. But they, by distributing that, allowed us to show that this method works. The details, again, are in our paper, but you can think of this as an application of the same regularization process that we used at Goddard for our typical Goddard product, except that we simplified it a little bit in order for this proof of concept to be a little more straightforward, and built a slightly simpler regularization for this particular paper. The proof of concept showed very good agreement with JPL and with Goddard. So two different Mascon solutions solved two different ways, and it showed great agreement for kind of all basins, which showed that this method works exactly as we would expect it to, and has a lot of promise. We also looked at how well does the Mascon solution remove errors from the original spherical solution. And so by taking the difference between our fast Mascons that we've created and the original ITSG GRACE 2018 spherical solution, we actually saw that the key differences between those two products is almost entirely noise and vertical striping, which means that this Mascon estimation process does an excellent job at removing noise and vertical stripes, but doesn't remove signal that we want to be able to actually study. So then to round out that paper, we took the method, we showed that it worked, and we said, let's apply this to two trade studies that can help us answer some lingering questions about past and ongoing Mascon solution development. So first, the Goddard and CSR Mascons map GRACE ranging measurements to Mascon space through that spherical harmonic expansion that I mentioned before. Now that expansion is truncated. So you have to decide, are you going to do a degree 60 expansion, a degree 90 expansion, degree 30 expansion, for instance? And there was a big question of, did our choice of where we expanded it to? And so typically Goddard has used a degree in order 60 expansion. Did that choice have any effect on how well we're able to recover the gravity field? So we did a trade study where we examined basin signal recovery across a whole variety of basins using spherical truncations as low as 30, and then all the way up to 96, which is what the ITSG GRACE 2018 product is distributed as. And we found that using an expansion to degree in order 60 or better captures most basins well, and that higher expansions only see marginal differences in most cases. There were a couple of very particular cases where a higher order expansion did a much better job, but by and large, anything from 60 and up was going to do a pretty good job coming up with the same answer. Our second trade study then examined the design of the Mascon regularization itself, and specifically looked at the effects of including off-diagonal constraints in the regularization. Now, when I say off-diagonal, what I mean is that when we do our least squares estimate, one of the things we tell it as prior information is that if two Mascons are next to each other and are part of the same kind of general area, so for instance, if both are land Mascons or both are in the Caspian Sea, then those Mascons should probably be somewhat related to one another. In this particular study, we did that by adding inter-Mascon correlations defined by the Gaussian smoothing function for various Gaussian smoothing radiuses. And then we also included constraints that said, okay, these are coastlines, and Mascons that are on either side of this coastline, so in other words, water versus land, should not have any correlation between them. And we found that when we combine these two things, the coastlines plus the little bit of correlation between neighboring Mascons, we can greatly improve the signal localization. And we found that you need a Gaussian smoothing radius of maybe 300 or 400 kilometers to perform best for most basins. On the flip side, what we found is that a diagonal regularization, so one where there is no correlation between neighboring mascons, there is no constraints that say land versus ocean and try and separate the signal that way, lead to a significant leakage across those boundaries. And so you can kind of see that in this figure. In the top left, we didn't try and put these correlations in. And you see, especially for the Caspian Sea, that signal has leaked outside of the basin. But as soon as we put those correlations in the other two figures there, top right and bottom right, we can see that the signal is able to localize inside of the Caspian Sea, that dark red spot right there in the middle. And we can also see that it's able to differentiate coastlines in many other places as well. So to summarize the paper, we can have a few key takeaways. First, it's now possible to estimate these rigorous mascons and their errors on a regular computer using standard scientific computing tools. We performed our analysis using Python's scientific computing packages, so 100% free. And we're preparing to do an open source release of that software. There's a whole process involved in that, but we hope to have that out sometime in the near future as kind of a reference implementation of this process. If you want to read more about the method, if you want to read more about our proof of concept or the trade studies, I encourage you to go find the paper in JGR Solid Earth. More recently, my colleague Bryant Loomis and some of his collaborators published a paper, I think it was in December of last year, examining a global application of a high spatial resolution technique for improving on like trends and annual signals and things that we typically study with GRACE. The method involves a direct estimation of things like trends, things like annual signals from the level 1B observations. Whereas typically, if we want to look at like a trend in the GRACE data, we typically go and look at all of our individual monthly maps, and then we calculate a trend from those monthly maps. The big kind of advantage of this new method that Bryant and others published is that they can actually now estimate the trends using all of that data that I was talking about before, and not being influenced by the processing steps causing us to lose information or anything like that. And instead accumulate 20 years worth of long track measurements in order to estimate just the trend or the trend and the annual signal. The big difference here is that we end up with much better spatial resolution. So whereas before it might have been something like 300 or 400 kilometer spatial resolution, now we might achieve something as good as 100 kilometer spatial resolution. And in this particular paper, what they were able to show was that this allows for much better agreement between GRACE surface mass estimates and solutions and ICESat or ICESat-2 based mass change estimates over ice sheets and glaciers. And so that's really important because we always want to have the best information available to us. And by using this new technique, we're able to go from the top right map, which is our monthly trend, down to the map right below it, which is this new higher resolution trend. And you can kind of tell that there's much finer detail, especially if you look out over the oceans. There's some kind of key highlights that really pop out a lot better, but then also over land as well, with the lower middle plot as opposed to the plot right above it. And then last today, I thought I'd just share a little bit of a highlight of some of our more recent work. This is unpublished, this is ongoing work, and it's really attempting to further bolster our GRACE estimation by doing a method called co-estimation, where we include both GRACE data and satellite laser ranging observations. So the motivation here is that we want to more rigorously determine GRACE mascons and hydrology-focused products. And to really understand this, we have to understand that typically all centers, when they're looking at GRACE data and creating GRACE products, create a GRACE estimate. But in that GRACE estimate, the estimates of C20 and C30, so that's Earth's equatorial bulge, and then also kind of what's often referred to as the pear shape of the Earth, two very long wavelength signals, are not that well recovered by GRACE. And so when we are looking at GRACE products, typically after estimating a solution, we remove C20 and C30 and then replace that with a C20 and C30 estimate from satellite laser ranging. The problem here is that we're doing a simple replacement in post-processing. And as you kind of might have gathered from the rest of this talk, we don't want to do non-rigorous things when there's a rigorous alternative, because anytime that you do any amount of replacement in post-processing or so on and so forth, we can affect the signal and the error in unpredictable ways. So instead, if we can find a way to co-estimate the mass cons with both pieces of information, we can fully incorporate all of that information together and properly account for errors in both of the solutions. And so with this slide, I'm just showing a comparison between 16 of the lowest degree coefficients from both GRACE and SLR. With GRACE, like I said, we can get out to thousands of coefficients to describe the gravity field. With SLR, we're typically talking about something like a 5x5 solution. Sometimes we add in C61 and S61, so maybe 30 or 40 coefficients at most. But you can see that for these lowest coefficients, they agree pretty well. These are coming up with the solutions using two entirely different methods. But we can also see that there are some differences there. And so these differences we can really examine and are manifest when we look at the errors associated with both of these solutions. In general, what we find is that GRACE performs better than satellite laser ranging, which is why, for the most part, we trust GRACE more than we trust satellite laser ranging in terms of resolving some of these higher degree and order coefficients. But we see that SLR performs markedly better for C20 for the entire GRACE and GRACE follow-on time history, and then also performs as well or better than GRACE and GRACE follow-on, kind of beginning in 2016 or so, and then moving forward. And it's important to understand a bit of the history of the GRACE mission, but beginning about June of 2016, there started to be some instrumentation errors and so on and so forth that caused a degradation in the GRACE product for that last year or so of its life. And then with GRACE follow-on, there have been some additional interesting problems that they have been working out new techniques to be able to account for. But kind of largely, the data is not quite as clean as it was during the best years of GRACE. Satellite laser ranging gives us this extra data point and actually can provide us new information about C30 that can really help our process. And we can see that for most other coefficients, GRACE performs markedly better, although you can see kind of a blip there at the end of 2016, 2017, where GRACE in general, which is the red line, sort of has all of these blips there, and satellite laser ranging all of a sudden becomes more important. So with all of that in mind, we took the fast mass-con approach that I described earlier, and we took the regression approach that Bryant published last year, and we actually found that there's a way that you can kind of combine the two. And so it's not a true regression. At this point, we're actually applying the same types of techniques as what was used in Bryant's paper, but now computing monthly mass cons, just like we always do, from both GRACE and satellite laser ranging. And we do this by combining the full normal equations of each, similar to how Bryant does his regression mass cons, but we do it on these monthly timescales, and we're able to estimate these combined solutions. When the combinations occurred, we have a GRACE plus SLR fast mass con, and the estimation process from there is basically the same as the fast mass con approach. And so, like I said, this is unpublished. It's an active area of research, but to close this talk, I thought I'd kind of show some of the early results from this particular co-estimation effort. So along the top, you can see that the trend and the annual amplitude recovered in the combined solution looks like what we might expect it to. This is doing a very good job. We can also see an example month from GRACE follow-on data. And kind of the takeaway message here is that we are performing as we might expect, but actually with slightly reduced errors, which is great. In the next line, there's a plot for C20 and below it C30. And we can see in these, if you look closely, that the GRACE only signal, which came from ITSG GRACE 2018, does not really contribute that much to C20, but it does contribute more to C30. And then the SLR solution almost totally contributes to C20 and then also contributes to C30. And so effectively, we find that doing this rigorous combination is allowing us to leverage both data sets for those particular coefficients. Now, we don't want to just look at how those two coefficients are affected. We want to look at how the entire combined solution is affected. And so we looked at the entire combined solution in spherical terms, and we considered the signal content of each of them. We subtracted the GRACE only signal from the combined solution, and we ended up with kind of the last plot that's shown here. There's a triangle plot that has lots of different flares in it, I'll say. The interesting thing with this plot is that SLR only contributed to the 5x5 gravity field, which in this particular plot means only the tiny point down at the bottom where we see like a flash of yellow. However, we see highlights, we see purple and yellow all throughout the rest of the triangle, which indicates that even though SLR was only directly affecting our low degree in order fields, it actually is helping to contribute to our understanding of the entire rest of the gravity field by driving down noise, so on and so forth. So having found that, we now need to dive deeper into this. We need to further investigate how those types of differences manifest themselves in like basin analysis, for instance. But overall, we believe that these combination solutions show great promise and are awesome for better resolving signals and reducing errors in our GRACE solutions. And this work is ongoing, and we're hoping to publish at least some of it and some of our findings within the next year. And so with that, I see that there is one thing that popped up in the chat, which I will check in a second, but I want to thank you. Here's my email address if you have a question that you don't want to ask right now. But I also want to, with however much time we have left over, and I don't have a clock right in front of me, I want to be able to answer any questions that you do have now.
Thank you, Mike. Matt Pritchard had to split halfway through, unfortunately.
Yeah.
So I'm gonna manage any questions that come through the chat or from the audience if I need to. So it's open for anyone to ask a question. I believe you can unmute yourselves at this point, but I'll check the settings just to make sure. Okay, try now. If you've been trying to unmute yourself.
In the chat, mine still says chat disabled in the chat, so I don't know if there's another checkbox.
Okay, one second. Maybe I need to do that. Ask all to unmute, play join. Chat, I thought show. Are people unable to chat? Thought I knew how to do this, Mike. Sorry.
Oh, it's okay. Maybe just nobody has any questions. That's fine too.
I have a question.
Okay.
If I cannot allow others, and that's not on purpose, I promise. I was wondering if, and this might be slightly off topic, but can terrestrial gravity measurements help increase, time series from gravity stations help increase the resolution of these products in the solutions?
Short answer is yes, they should. That's something that we would like to investigate. However, I think we are hoping that we can partner with, people that are experts in particular terrestrial measurements. So one thing that we have talked about is that including GPS measurements, for instance, of vertical displacement could really greatly help us improve the spatial resolution over areas where we know there's a lot of local variability. One of the things that we have to consider when we're looking at the MassCon products I was talking about today is that we tend to resolve these in 1 arc degree MassCon space, so about 110, 112 kilometers on its side, which is higher than the nominal resolution of GRACE, but still significantly lower resolution than a lot of the things that people might be interested in. And one of the interesting applications of the FastMaskCon method that we have started to explore is how to push that resolution essentially to infinity. And the real benefit of doing something like that would be in including terrestrial measurements or models or any other type of data set that would allow us to have better localization. The other thing that's nice about that is we could potentially have really high resolution in some locations where we have that type of data, and then not need to go as high resolution in other locations, which would be pretty interesting.
Yes, definitely. Okay, I think I found the setting that allows people to chat to everyone. So hopefully they actually can, and I'm not just fooling myself. But wait, I see someone starting their video. Ashley?
Yeah.
Okay, great. Go ahead.
Great. Yeah, glad that I can start my video to ask the question. Thanks for a great talk. I really enjoyed it. I was wondering, can you give me an idea of how computationally expensive the work that you do is? And I was also curious about what coding language or languages you work in to do this.
Yeah, that's a great question. So I'll give you a comparison. With our kind of what I'll call the traditional rigorous methods that we use, if we want to do a new solution from scratch, that means we have to process all of the level 1B data, do all of the intermediate calculations, and then iterate on that, and we eventually get to our MaskCon solution. When we want to do something like that, that can be a multi-week process on a big cluster that we have at Goddard. That by itself was a huge motivation for when we realized the FastMaskCon method existed, we wanted to explore it and publish it. And what we found is that that method, like I said, it allowed us to decouple a lot of that early processing stuff. And now the kind of core part where we're able to say, okay, we want to add in prior knowledge that we know, we want to combine it with terrestrial products like what Bill was just talking about. That can be done on a MacBook computer in the matter of, depending on if you want to do, you know, monthly solutions, or if you just are interested in one particular year or whatever, it could be done in anywhere from 10 minutes to say 6 hours. And what that means is that we can iterate on the design, we can add in additional information, we can, you know, figure out new ways to resolve what we're looking at much more quickly. Whereas if we have to do it on this 2-week time frame, then you kind of are limited with what you can do. As far as the languages we use for the kind of paper that I presented there and the proof of concept, that was Python, NumPy, SciPy, Pandas, and Xarray. And you know, if I had tried to throw it at a big cluster, I could have probably done it in under an hour. My MacBook computer, I will say, the best thing you can do in order to do these quickly is have as much RAM as possible. My MacBook computer has 32 gigabytes. If I'd been limited to 16, then I probably would have been limited in my solution to the degree in order 60 expansion that I talked about before. That would be on par with what we've been producing as a center. So that's not even bad. But with 32 gigabytes of RAM, I can go out to that 96 degree in order solution, which is estimating 9,400 different things at the same time. And I still have RAM to spare. And so, yeah, I mean, this really is the type of thing, and this is why we want to try and get this software out into open source. This is the type of thing that anybody on you know, even any grad student could take this and go and investigate some particular problem of interest. Let's say they're focused on some very particular part of North America or something, that as a center, while we're producing our, you know, rigorous traditional MaskCons, we can't take the time to focus on all of those individual things. Now, every scientist could if they want to, and that's huge.
Well, that's a lot more impressive than I even expected.
Yeah, I was a little surprised at how well it performed, if I'm being honest. Bill, I see a question in the chat, so I'll just read that out loud. This is from Christian. Can a sea level change rate be derived from GRACE data? Yes, with a asterisk. So sea level rise is caused by two key processes, I'll say. The first is water actually being added to the oceans. So that's a mass change, and GRACE can see that. And so we can estimate a global mass contribution to sea level rise. The second contribution, though, it has to do with temperature and salinity differences. And so as the oceans warm, for instance, we can kind of think of the oceans as a giant thermometer. And when a thermometer gets warm, the mercury in the thermometer rises, it expands. Well, over the oceans, as the oceans warm, the oceans expand. And GRACE can't see that because that's not a mass change effect. And so what we can do then is use a mission like there's a particular set of floats that are out in the ocean called the Argo floats. They are all across the ocean and they dive down to 2,000 meters deep and they take measurements of temperature and salinity. And we can use that to determine the height change of sea level from temperature and salinity changes, combine it with the mass change from GRACE, and you get the total thing. Then if you wanted to compare that, the other direct way to estimate sea level, one way would be through satellite altimetry. And so the TOPEX and JASON missions and now more missions beyond, especially from Europe, are doing that with radar altimetry. And that gives you a direct measurement of the total sea level change height. So something that we actually do as part of the GRACE science team is we look at how well is that combination of GRACE plus Argo comparing to altimetry. And when we see differences, we start to analyze, okay, why are these different? Is one of the instruments causing a problem? Is there something that's not being modeled correctly? Or is there, something that a difference in the actual observations themselves that we need to account for? So great question, thank you.
All right, are there any more? Okay, great. Mike, thanks so much.
Yeah, thank you, Bill.
That was wonderful. I'll remind everyone that this has been recorded and eventually it'll be, a file will be created that can be posted to YouTube, and we'll check in with you about that, Mike, afterwards.
Okay.
And so folks can go back to it and refer to it or show their classes some of these great results. So thanks, everyone. This is the last talk of the season for the AGU Geodesy Section early career lecture, but we're hoping to get it going again next year. So thanks for attending.
All right, thank you.
See you
Have a great day.
So long.